Welcome to Massive Open Online course on basic principles and calculations in chemical engineering. So, we are discussing about fundamentals of material balance with examples under module 3. In this lecture, we will discuss that material balances on reactive processes. Here, we have given earlier the examples of material balances with non-reactive processes like with recycle, with bypass and with bypass. Here, we will discuss something more about that reaction processes like selectivity, yield, extent of reactions, and how this extent of reaction concept can be used to do the material balance on this reactive processes. Now, before going to that calculation, you have to know some terminology of that reactive system. In this case, to consider chemical reactions, you have to know the stoichiometry of that reaction equation. Now, you know that theory of the proportions in which chemical species that combine with one another in a reaction as represented by an equation, and that will be called as equation of reaction. And actually this that concept of this that reaction equation with that stoichiometry generally originates from two Greek words, that is stoichein, that is called element, and metron, that is called measure. So, based on this stoichiometry is coming. Now, this stoichiometry actually for a particular reaction equation, it will provide a quantitative means of relating the amount of products that produced by chemical reactions to the amount of reactants. Whereas, in this stoichiometry you will see that to this stoichiometry you will get that stoichiometric equation that will give you the statement of the relative number of the molecules or moles of reactants and products, but not mass, you can say, that participate in the reaction. And the coefficients actually represented by the numbers that will be preceding each species in the balanced in the reaction equation. And stoichiometric ratio, this will be actually regarded as the ratio of stoichiometric coefficient of any two species. So, these are some terminology that you have to remember and you have to understand. And also in a reaction you will see some reactants will be limiting reagent or reactant. In that case, that reactant that would be first depleted if a reaction proceed to combustion and proceed to completion. A reactant is limiting if it is present in less than its stoichiometric proportion relative to all other reactants. Now, in this case you have to identify that limiting reactant. Now, how to that identify that limiting reactant there? First of all, you have to select the reactant with the lowest stoichiometric coefficient in a particular reaction, and if there is more than one reactant with same lowest coefficient, example like this given here in this slides. So, in that case you have to select the one with the smallest number of moles fed. After that, you have to set up the stoichiometric ratios with the lowest stoichiometric coefficient that will be identified as the denominator, and in doing so all your stoichiometric ratios should be greater than 1. After that, you have to set up the corresponding ratios using actual feed values. So, all these things earlier also, because you have already completed all those things in your schools levels, also in higher secondary schools there. Still you just go through this concept for your understanding for further calculation in the material balance. Now, in that case you will see that with that limiting reactant, how to actually find out that which one will be the limiting reactant. In that case, if you compare each set of ratios like here Nx by Ny, that will be in the feed, versus Nx and Y that will be in the stoichiometric. So, if Nx by Ny in the feed is greater than equals to Nx by Ny in the stoichiometric coefficient, then you will see that the reactant X will not be limiting. Whereas, if Nx by Ny in the feed, if it is less than Nx by Ny in the stoichiometric coefficient, then you will say that X will be limiting reactant. Other terms like fractional excess, sometimes you will see that to complete the reaction you have to supply some excess reactant there based on its limiting reactant. And also sometimes the what will be the amount of reactant will be supplied in the feed, you have to calculate what should be the actual amount of reactant amount is required for your complete reaction theoretically, and after that you have to judge what should be the excess amount of that reactant is present in your feed mixer, or if it is shortage then you have to supply excess amount of that reactants in the feed mixer, so that your reaction will be completed. Now in that case you have to assess that concept of that excess reactant based on this fractional excess equation here. So in that case fractional excess will be calculated as here F excess, that will be equal to what will be the number of feed of that species I, and also what will be the number of moles of I that is required for your complete combustion, that you have to calculate. And after that if you divide it this that difference of that species present in feed and species required for your complete reaction theoretically, if you make a ratio then it will be called as that fractional excess, where I will be the excess reactant here in this reaction here in this equation. Now if we consider an example of reaction like this here, it is given in the slides. In this case see here A is reacting with B and gives you that C and D. In this case here coefficients, stoichiometric coefficients are 1, 11, 7, 8 respectively. Now in this case given 1 mole of C7H16 and 12 mole of oxygen, in this case you have to identify what should be the limiting reactant. Now you have to find out first what should be the ratio of that oxygen to here heptane in the reaction, then as per stoichiometric coefficient this ratio will be coming as 11/1, whereas the ratio of these molecules in the feed it will be 12/1. Now it is simply that this 11/1 is less than 12/1. So we can say that oxygen in excess here. So oxygen is excess here. So we can say that oxygen in excess, but the limiting will be that other one, that is C7H16 here, because in this case you will see that this C7 if we compare that it will be less than that feed. So accordingly we can say that this C7H16 is limiting, and where what is the fractional excess of that excess of that limiting reactant here as per that equation earlier given here like this, accordingly you can get what should be the excess of that limiting reactant. So this will be your 0.09 in this case. Other definitions, like suppose there are two reactions A plus B which will give you C and D, and C plus B which will give you E and D. Now further reaction of desired product C, undesired reaction will be there in a particular set of reactions. Now in this case if C is the desired product, then you have to minimize the second reaction from taking place, and also second reaction uses up reactant B and desired product C. It also produces undesired product E. Let A be the limiting reactant here. So conversion of A will be equal to mole of A reacted by mole of A feed, and conversion of B will be represented by mole of B reacted by mole of B fed. And you can select that which component will be that desirable or undesirable based on that selectivity. So that selectivity will be defined as mole of C in output by mole of E in output as per that reaction, and yield will be defined as here this total mole of products by total mole of A feed. and yield of C for particular species, then you can say that mole of C in output by mole of A feed, and efficiency of the product output of C will be is equal to mole of C in output by mole of A reacted. Now, in this case the term yield and selectivity are used to describe the degree to which a desired reaction predominates over competing side reaction. Another important terminology that you have to remember, sometimes it will be required for your material balance calculation based on reactive system. Now, in this case if we consider that certain process unit reactor where reaction is going on and A will be giving to B, in that case A is coming at a certain flow rate after mixing with its recycle here, and it enters to the reactor at a certain rate, and after that reaction it will give you the mixture of unreacted A and the product B, and there will be a certain flow rate of that A and B, and after that it will be coming out and it will be separated in a certain process unit, and then as a product you will see that some amount of product as a pure B here it will be taken, but remaining unreacted that reactant will be sent back to its mixer before process unit of reactor there. So, here in this case one interesting term that you have to know, that overall conversion of the A, how you will define it. Now, for overall conversion of A you have to consider that whole process here. Whole process means including that mixer, reactor and separator. So, in that case this overall conversion of the A will be represented by what should the input of A and what should be the output output of A there, and divided by input of A. So, here you will see that input is coming as 100 mole per minute, whereas output is that there will be 0 for specifically for component A. So, here 100 minus 0 by 100, that will be into 100, then that means here it will be 100% overall conversion. Whereas, if you are considering that there will be a single pass conversion, that means here what will be the input of A in a particular process unit like here reactor. In that case only you have to consider here the reactor. So, for the reactor what is the input of A, and for the reactor what will be the output of A. So, in this particular example you will see that the input of reactor for this component A is 100, whereas output of component of this A only for this reactor it will be only 25 as shown here in the figure in the slide. So, you can calculate that single pass conversion of A will be equal to 100 minus this 25 divided by that 100, that means input. So, input minus output divided by input, that will be regarded as single pass conversion of here particular species. So, here it is coming 75%. So, what is comparison, that overall conversion and single pass conversion will be totally different. Overall conversion as per here it is coming 100%, whereas single pass conversion it is coming 75%. So, this sometimes this concept will be sometimes required for your material balance calculation in the reactive system. Now, another important aspect of reactive system that actually sometimes at a particular time what will be the amount of reactant is present in the system, and what will be the reactant conversion, and after conversion what will be the amount of reactant will be present in the system, that also represented by certain concept. It is called extent of reaction. Now, consider the reaction A which will give you the product B. So, in this case if you assume that an infinitesimal amount of d xi, here one xi is considered here, some d xi amount of that reactant A, that changes into B. So, we are considering that some amount of A is converting to B, that some amount of reactant will be denoted by this d xi. Now, this change of this amount of A can be represented by the equation here. This dNA will be equal to minus of d xi. The change of B similarly can be expressed as dNB will be equal to d xi, because same amount of A will give you the product B here. So, dNB will be equal to d xi. Now, similarly, the extent of reaction is then defined as d xi will be equal to what will be the change of that component I with respect to its stoichiometric coefficient, that will be divided by here nu I. Here Ni denotes the amount of ith reactant, and here nu I is the stoichiometric coefficient of the ith reactant. So, in this way you can define that extent of reaction, and other way it can be defined as like it is the amount of substance that is being changed in an equilibrium reaction. Considering that finite changes instead of infinitesimal changes, one can write the equation for the extent of a reaction as delta xi, that will be equal to delta Ni by nu I. Then it can be written as Ni0 minus Ni by nu I. So, here Ni0, that may be that equilibrium concentration, that is at the outlet, or at a certain time when it will be coming as equilibrium, that equilibrium moles will be there n, and initial moles will be n I initial, you can say that, and divided by its stoichiometric coefficient. So, in this way you can define that extent of reaction. The extent of a reaction is defined as 0 at the beginning of the reaction, because in that case the changes of xi is the extent itself there. Now, that extent of reaction for multiple reaction, how to calculate that. In that case, that for multiple reactions this extent of reaction based on which you can derive this equation as Ni, that means at a particular time what should be the moles of I present in that process unit, that will be equal to Ni 0, that means what will be the amount of I fed in the feed mixer, and what will be that summation of Vij nu Ij into xi j. So, nu Ij here stoichiometric coefficient of the reaction, here j, if there is a j number of reactions are there, then you have to consider that nu I for particular reaction. And similarly, the extent of reaction for that reaction J will be denoted by xi j. So, accordingly this equation will be used for that extent of reaction calculation for a particular reaction. Now, in this case very interesting that you have to remember the stoichiometric coefficient will be treated as a negative for the reactant and positive for the product, that you have to remember. Now, let us have an example for this. Now, if water gas shift reactor like carbon monoxide plus water will give you that carbon dioxide and hydrogen gas, that will proceed to equilibrium at a temperature T Kelvin. Now, the mole fraction of the 4 reactive species satisfy the relation here, it is given Y carbon dioxide into Y hydrogen divided by Y carbon monoxide into Y water, that will be equal to some equilibrium constant. Now, this equilibrium constant it is regarded as reaction equilibrium constant at time, that is 1105 Kelvin, this K will be equal to 1. Now, at this condition, suppose the feed to a reactor contains 1 mole of carbon monoxide, 2 mole of water, and no carbon dioxide or hydrogen, and the reaction mixer comes to equilibrium at 1105 K. So, in this operating condition of this reactor, you have to calculate the equilibrium composition and the fractional conversion of the limiting reactant. So, here this YCO2 is represented by mole fraction of carbon dioxide and Y H2 is mole fraction of hydrogen, YCO it is mole fraction of carbon monoxide, and YH2O is simply that mole fraction of water. So, based on this at equilibrium condition, what should be that equilibrium concentration of this carbon monoxide, water, carbon dioxide and hydrogen, that you have to find out. So, you have to use that concept of extent of reaction here. Now, let us solve this problem here. As per equation, we know that since here only one equation here. So, if we apply this general equation for multiple reaction here, in this case J will be equal to 1 only. So, Ni is equal to Ni 0 plus summation of nu Ij into Jij. Here J only 1, that is one reaction is there. So, in this case if I consider only for carbon monoxide first, then here Ni, that means here N carbon monoxide, that will be equal to what, what will be the feed amount of carbon monoxide, it is 1 mole, whereas at equilibrium condition that extent of reaction will be equal to Ji. Now, in this case here as per reaction here, what is the reaction equation is given, carbon monoxide part here, this is CO2 plus water, that will be giving you what is that, carbon monoxide, carbon dioxide here, this is CO plus CO plus water, that will be equal to CO2 plus hydrogen. So, this is your reaction. So, in this case you will see that if we consider that carbon monoxide, so in the feed this amount of carbon monoxide is here 1.00 mole, and here we can say that at equilibrium condition this extent of reaction is Ji. So, here for Ji we have to consider this nu here as minus 1, because this is reactant. As we told that for the reactant this coefficient to be considered as negative, whereas for product the consideration will be positive. So, here in this case this carbon monoxide, it will be then represented by this equation here, NCO is equal to 1 minus Ji. Similarly, for water again you can consider here this coefficient is I think here H2O here, this the feed amount is here 2 moles is supplied in the feed, then N H2O will be equal to 2 minus Ji. Again here this coefficient is 1, so it will be negative of 1, then it will be minus 1 Ji. Similarly, for carbon dioxide, if we represent it, it will be only here Ji. Here in this case coefficient is 1, that will be positive since it is a product, but here since there is no amount is supplied in the feed mixer, so Ni 0 will be equal to 0 here, whereas similarly for hydrogen it will be represented as Ji. Now, after that you have to calculate what should be the fraction in terms of this Ji. Now, what should be the total amount of moles, that first you have to calculate, that you have to sum it up all those things, and then you have to divide individual moles with that total moles, then you will get that concentration. So, here like this if you sum it up this whole moles here, you will get here simply 3 moles only. So, this is total mole is 3 moles. Now, then Y carbon monoxide will be represented by this, and similarly Y hydrogen will be like this, and Y carbon dioxide will be like this, and Y hydrogen will be like this, because here this is simply mole fraction. Now, after substitution of mole fraction of all these components, carbon monoxide, water, carbon dioxide and hydrogen, you will see that this that in this equilibrium equation, then you can have this final form of equation after simplification, and then after solving you will see that Ji will be equal to 0.667. So, this is called extent of reaction at its equilibrium condition. Now, after substitution of xi, here again in this mole fraction of each component, you will see that this mole fraction of component carbon monoxide, it will be coming as 0.111, and mole fraction of water, it will be coming as 0.444. Here just substituting the value of xi. Similarly, for mole fraction of carbon dioxide, you will get after substitution of xi here, and then hydrogen, for hydrogen you will get this that after substitution of xi here. So, finally, you can get this mole fraction of carbon dioxide as 0.22 and hydrogen would be equal to again 0.222. So, these examples will give you how to calculate that composition of components in the mixture when it will be as per a certain reaction with its output or products at a certain equilibrium condition. Now, what should be the limiting reactant in this case? That if you verify that principle based on earlier equation that I have discussed. So, it will be that the carbon monoxide will be as limiting reactant. Now, at that equilibrium condition, what should be the carbon monoxide moles that can be calculated here, that is what is the feed mixture and what will be the equilibrium mixture concentration. So, it will be here simply you can say that NCO moles in the mole it is given here, what is that 1 mole, whereas at the equilibrium condition it is coming 0.66 mole. So, based on that we can say that here it will be at equilibrium condition it will be 0.333 mole, and then fractional conversion of carbon monoxide at equilibrium will be as FCO, that will be equal to 1 minus 0.33 mole carbon monoxide that will be reacted divided by that 1 mole of carbon monoxide fed. So, it will be coming as 0.667. So, this is your fractional conversion of carbon monoxide. So, we can easily calculate based on that extent of reaction concept what should be the fractional conversion of carbon monoxide and what should be their equilibrium composition in the mixture. Let us do another example of this with multiple reactions. In this case, if we consider that a reactions as follows take place in a continuous reactor at steady state condition in a reactor. So, we can say that here this is one reaction, that means here ethylene ethylene is given that by this that by this conversion of ethylene. So, ethane is actually obtained by conversion of ethane. So, ethylene is obtained from the conversion of that ethane at a certain temperature and pressure, and also it will give you the hydrogen, and then also you can say that this that ethane again reacting with that products hydrogen, it will give you that methane. So, in this way based on this multiple reactions, how to calculate that that molar composition of the product gas and the selectivity of the ethylene to methane production, that we can actually obtain by that concept of extent of reaction. So, let us have this reactions that is going on in a reactor and that and the feed contains 85 mole percent ethane and 15% inerts, and the fractional conversion of ethane is given 0.501 and the fractional yield of the ethylene is given is 0.471. So, as per this schematic diagram here or flow chart, you can say that means here if we consider that 100 mole of mixture is going into the reactor, out of which that 8.85 moles per mole of feed it is, that means here 85% mole of ethane and 15% only inerts are going into the reactor, and after reaction happens you will see them some ethane then some amount of ethylene, some amount of hydrogen, some amount of methane, and along with inerts will come in the outlet streams as a product. Now, in this case very interesting that this inert components will not take place in the reaction. So, whatever amount of inerts will be going to into the reactor, that amount will be coming as in the outlet streams. So, that should be considered. So, if I use that concept of that extent of reaction for the multiple reactions, then this is your governing equation. Based on this equation you have to calculate all these things. Now, let us consider that N1 according to this here that flow chart. N1 is for C2H6, that means ethane, N2 for ethylene, and what is that N3 for hydrogen, N4 for methane, and N5 for inert amount in the outlet streams. So, in that case if we use this this extent of reaction equation here, so N1 can be represented by this here. What will be the feed amount is 85 mole, whereas as per this summation of V nu Ij into Ij. So, if you substitute that, the coefficient is 1, since it is a that in the reactant streams, and then coefficient will be negative. Similarly, in the first reaction it will be negative of 1 to Xi1, and similarly for the second reaction it will be negative of Xi2. Similarly, for N2 you can represent it as N2 will be equals to Xi1, since it is a product, then you have to represent this coefficient eta sorry nu as positive terms. So, it will be positive 1 Xi1 here as per equation. Similarly, N3 will be equal to Xi1 minus Xi2, and N4 will be equal to 2 Xi2, and N5 is equal to this 15 moles, since it is not taking part in the reaction, and the same amount of inerts will be coming into the outlet stream as what it is given in your inlet stream. So, based on this concept of extent of reactions, we are getting this N1, N2, N3, N4 and N5. Ethane conversion, if we consider that if the fractional conversion of the ethane is 0.501, it is given in your problem, the fraction unconverted and hence leaving the reactor must be 1 minus 0.501. So, finally, you can calculate what should be the N1. So, N1 will be coming as simply up to 42 mole C2H2. Now, this N1 actually is as per that extent of reaction, it is simply 85 minus Xi1 minus Xi2. Similarly, ethylene yield will be actually represented by this equation. It will be coming as 85 moles as per definition. Then N2 will be actually defined as like this one 0.471 into 85, then that will be equal to as per extent of reaction concept, then 40 mole of that means here ethylene, that will be equal to Xi1. So, finally, you can get that this Xi1 will be equal to here simply N2, that is amount. What is the amount here? That will be 40 mole of ethylene there. So, Xi1 we have calculated, and it will be as what is that N2, and this amount is 40. So, substituting this 40 mole for Xi1 in equation number 1 here given. So, we can get that what should be the value of Xi2 there. So, Xi2 will be equal to 2.6 mole. Then after substitution of Xi1 and Xi2 in N3, then you can get that here in N3. N3 is basically Xi1 minus Xi2. So, after subtraction of Xi2 from Xi1, you can get this N3 as 37.4. Similarly, N4 you can calculate like this to Xi2, so it will be coming as 5.2, whereas N5 is already known to you. And then total mole will be is equal to C, that will be summation of all the N1, N2, N3, N4 and N5 in the outlet stream. It will be coming as total amount 140 mole. So, after that you can easily calculate what should be the fraction of all those components there. So, it will be simply individual amount of that component divided by total mole, then you will get that fraction of that individual components. So, it will be coming as 30.3 for ethane, 28.6 for ethylene, and that 26.7% for hydrogen and 3.7% for methane, and remaining 10.7% for inert in the outlet stream. And based on this you can calculate what should be the selectivity. That selectivity is defined as what will be the mole of ethylene produced based on what will be the amount of that methane byproduct is produced there. So, this is simply 40 by here 5.2, then it is coming 7.7 mole of ethylene based on that total mole of methane in the outlet stream. So, this is the concept, also how to calculate that selectivity, and also what would be the mole fraction of different components in the outlet streams based on the multiple reaction. So, please go through these examples and practice it, and then you will be able to solve other different problems based on that multiple reactions. So, I would suggest you to follow this concept of that extent of reactions in these books, like first textbook here Felder and Rosu. They are elementary principles of chemical process, 4th edition. You will get more information about this extent of reaction there, and please practice some example problems given there also. So, thank you. So, next lecture we will try to describe more material balance based on reactive system, even with multiple unit with recycle, bypass, and even makeup, and also some combustion reactions, how to do the material balance on them. So, thank you.